Today we're looking at growth and decay problems. Our goal? Solve growth and decay problems. There's going to be three equations we're going to work with for three different situations, so you'll know which situation works with which equation. Our first is compound interest. Compound interest involves a principal P, that's the amount of money you invest, an annual rate R, that's your interest rate, is compounded n times a year for t years, and that'll grow to some amount A. R is always a decimal, so your rate is implied as a decimal, n is the number of times you're compounding it, t is how often you're compounding it, or how many years, A is your final amount, and P, again, is your principal, the amount you invest. So let's use this problem. How long does it take for an investment of $1,000 to triple in value if it is invested at an annual rate of 12% compounded quarterly? So, in this case, P is 1,000. Your final amount, or your goal, is 3,000. Your rate is 12%, or 0.12. And the number of times per year you are compounding it is 4 times per year. So let's throw this into the formula. 3,000 equals 1,000 times 1 plus the rate, 0.12, over the number of times you're compounding it, 4, because it's 4 times a year. And that's all raised to the 4t power. We're looking for t. We're looking for how long, so we're looking for time. So I'm going to divide both sides by 1,000, and that's going to get me 3 on that side, and 1,000 is going to become 1. And I'm going to add 1 plus 0.12 over 4. 0.12 over 4 is 0.03, plus 1 is 1.03, all raised to the 4t power. Next, I'm going to use logarithms. The log of 3 equals the log of 1.03 to the 4t power. The reason I'm taking the log of both sides is now I can move 4t out of the exponent. Log of 3 equals 4t log of 1.03. And I'm going to divide both sides by 4 times the log of 1.03 to get t equals the log of 3 over 4 times the log of 1.03, which is about 9.3 years. So if I want to figure out how much or how long it will take me to triple my original investment, it'll be about 9.3 years, but since this interest is compounded quarterly, I have to go by quarter years, and 9.3 is closer to a quarter than it is to a half, so it's about 9 1/4 years. So it's about 9 1/4 years. That would be my final answer. So this is the doubling growth formula. This happens a lot with bacteria or populations of people, and this is represented thusly. N sub 0 is the amount of you start with. So this is the starting amount. And it should double every d years. So this is the doubling time. Our final amount, n, after t years, is given by this equation. So t is the number of years. And it's n equals n sub 0, my starting amount, times 2 to the t over d power. Let's use it. A bacteria population doubles in size every 12 hours. How much will it grow in 2 days? So we're going to use this formula. In 2 days, there are 48 hours. So t is time in hours, so we're going to use 48 hours. D in this case, is 12 hours. Because we want the units to be the same, and if it doubles every 12 hours, let's keep our units the same, 48 hours, 12 hours, it works out nicely. We don't know how much there was originally, but we can figure out by how much it will grow. If we use the equation, n equals n sub 0 times 2 to the, it's t over d, so 48 over 12 power. So let's simplify that. N equals n sub 0 times 2, 48 over 12 is 4th, 2 to the 4th is 16, so n equals 16 n sub 0. So after 2 days, it'll grow by a factor of 16. It'll be 16 times bigger. Or 16 times larger in 2 days. Finally is the half-life decay formula. Your science teachers are going to love the fact that you've watched this video, especially your chemistry teachers. A lot of this comes out of carbon dating. Carbon dating is a way of measuring how old something is. You look at the amount of carbon-14 left in something. So what this formula represents is n sub 0 is your amount. The half-life, H is called the half-life. And what half-life is how long does it take for half of that thing to disappear. So since carbon-14 is radioactive, it's how long does it take for half the radiation level to be gone. And that takes, for carbon-14, quite a long time. So you're going to have some pretty big numbers here. There are other isotopes that you would use. Carbon-14 happens to be the most frequent one you do use, but they're usually pretty long half-lives, unless you're talking something that's quick, but that doesn't happen very often. So H is the half-life, T is time, as always. N sub 0 is your starting amount. And N is the amount you have after half-life takes its effect. So what we're going to do is solve this final problem. The half-life of carbon-14 is 5,730 years. Told you it was a long time. How much of how much of a 10 milligram sample will remain after 4,500 years? So before we even start, since 4,500 is less than 5,730, we should have more than half remaining. So we know that we should have more than 5 milligrams left. That should just be instinctual at this point. But let's plug the numbers in. N sub 0 is 10 milligrams. We start off with 10 milligrams. The half-life is 5,730 years. The time we're talking about is 4,500 years. They're in the same unit, so that's good. Let's take these and plug them into the formula. When we do this, we've got N equals 10 times 1/2 to the, it's T over H, so 4,500 over 5,730 power. Now, I may be a math teacher. I can't do that in my head. So what I did was I plugged this into the calculator, and I found that N equals 5.80, and that's to the nearest 3 significant digits. So there is 5.80 milligrams left after 4,500 years. They're the 3 biggest types of word problems you'll find. Each has a formula. So just figure out what the question's asking, which formula do you need to use, and there's your answer.